All right, so welcome to part 2. So we've introduced the equation for thermal energy. Let's figure out how to take that and plug it into the conservation of energy. So this here is the really super formal version of the conservation of energy with friction. So we have the change in kinetic energy is equal to the change in the potential energy plus the change in thermal energy is equal to the change in the system, which is equal to the external work being done on the system. Now, as I previously mentioned, we're not really going to be dealing with external work, right? We looked at that picture and it had just change between kinetic, potential, and thermal energy, where we can only gain thermal energy. So what that means is we're going to be dealing still with isolated systems. So there is going to be no external interaction, and we could rewrite our conservation of energy as such. So our external work is going to 0, our energy of the system is going to 0, and we're going to isolate the initial and final values. So the reason we have the change in thermal energy on the final side is at our starting position, so ETH I, let's call it, is going to be equal to 0. We have no starting thermal energy value. We don't care about what happened before this particular question. We only care about what has happened from the starting point to the final point. I don't care about anything before. I've probably generated some thermal energy to create this, but I don't care about it. Only looking from initial to final, point 1 to 2, 2 to 3, 3 to 4. I'm looking at it point by point. Now I want to make it very clear that when we are dealing with the final value, it is plus change in thermal energy. So we could have change in kinetic energy plus change in potential energy. That is the change in thermal energy. So when we then separate the initial and the final, it goes back to this equation here. So it's kinetic energy, initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy plus any thermal energy that is generated. This is going to result in the conservation of energy holding true. We need to make sure we are adding the thermal energy to the final side of the conservation of energy to ensure we have the total energy being conserved. We must keep thermal energy as positive on the final side. The reason I am repeating this so much is the second friction gets involved, in about half of the cases when the question is wrong, it is because they subtract thermal energy. We are not losing thermal energy, we are gaining thermal energy between our starting and ending point. That is why we have to add it. We are gaining thermal energy. Gain is positive. So again, just make sure that you are using positive thermal energy when it is on the final side of the equation. So let's do an example. So I'm not going to have you pause the video for this one. I'll have you do that for the next one. But we have a student here who is very foolishly volunteered for this. If I did my calculations right for how fast this person would accelerate, it would kill them. So if somebody asks you if you want to be attached to a spring that has 80,000 newtons per meter, no, don't do that. Do not recommend in any way, shape, or form. So let's read through this question, and I'm going to highlight the key aspects that are going to be important moving forward. So we have a spring constant, so that's going to be important because we're compressing it 50 centimeters. So I'm going to use blue for constants throughout the question. I'm going to try to use different colors for the different points. So we have point 1 That's not very visible. Point 1, where the student is compressing the spring. That's 50 centimeters. And is used to launch the student, which is 100 kilograms. Again, the student is probably not going to make it much longer after this question, so might as well make it a nice round number. The track is frictionless until it starts up the incline. So the way that I like to make sure that I keep track of friction correctly is I like to draw this little squiggly line that indicates that this is where friction is. Everywhere else is going to be nice, smooth, and ideal. I have an angle of 30 degrees for my incline, and I have my coefficient of kinetic friction as 0.15. So my first point I've already marked as my student compressing the spring because I was given an unknown for that. So then we want to find the student's speed just after losing contact with the spring. So that means that before they go down the hill, so as they are no longer in contact with the spring, I would like to calculate the speed. So that is going to be my point 2. I then have the point where how far up the incline the student goes. So somewhere over here, my student is somehow alive. Their tushy might be a little bit on fire, but they're over here, and they are at 0.3. So before we go any further with this, I want to make something clear about how textbooks word questions associated with going up inclines. So here it says, how far up the incline? Right? This is how the question is worded. So we are actually solving for this length here. This is how far the student is traveling along the incline. It is not the height, it is the length of incline that the student is traveling. So we are solving for L, not Y, in this question. So these are the 3 points in which the textbook question is asking about. We have everything about point 1. We need to calculate the speed, and eventually we want to go up the incline. So these, if we want to have as few points as possible, these are the points we would need to consider. Now, it is perfectly valid to instead, I don't want to use purple, I already used that, to say, well, I want 0.3 to be the bottom of the incline and 0.4 to be up the incline. You are welcome to do it this way if you want to, but it's going to add an additional step to your question. We don't ever actually care about the bottom of the incline. It's never important for this question because our student, I'm going to guess based on the picture, they are bigger than 50 centimeters. Or at least their legs are longer than 50 centimeters. That's pretty small. So they're going to stay on that top for a while. Now also in this image, we're getting one more piece of information. We are given the height that the student is starting at. So when we have pictures associated with problems, it's going to be very beneficial to look and make sure that we don't have any extra information given to us in the figure. All right, so we can go ahead and we can set up that table. So I'm going to only look at it for the 3 points. So I'm going to have 0.1, 2, 3. Give myself a little more space. And then I'm going to have my speed, my Y value, my X value, and do I have thermal energy? So with this, I'm just going to check yes or no if I have thermal energy. So if I look at 0.1, my value is going to be 0 because my student is at rest. The same is true for 0.3. I am at rest in these given locations. So 0 there. I don't know what V2 is, and that's what I'm solving for in part A. So if I know that, why am I solving for it? If I look at the height, so for points 1 and 2, I'm staying on top of the original hill. So I have a height of 10 meters, and I don't know the height I have for 3. So I don't know Y3. For position 1, I know I'm compressing the spring ½ meter. For position 2, I'm no longer attached to the spring. And for position 3, I'm still not attached to the spring, so it doesn't matter. I, the student, whatever, is no longer attached to the spring. Boom. There is no friction until 3. So that means that my change in thermal energy for 1 and 2 is going to be 0. But I do have a value for 3. So this is going to be how we can go through and set up the question. For part A, I'm going to be using only 1 and 2 because I haven't gotten to the point where I'm at point 3 yet. For part 3, I'm going to be using points 1 and 3 because I have everything explicitly given for point 3, or sorry, for point 1. And I personally like to use exact values as much as possible when going through and solving these questions. So I am now ready to go through and solve. So let's go ahead and do part B, which is what is the student's speed after losing contact with the spring? Sorry, this is part A. So let's write out the types of energy that we have. We could have 1/2. So let's write out the formal name of the conservation of energy. So right, we have all of our energies at point 1 is equal to all the energies at point 2. Plus mg y2. Because I don't have thermal energy at all between points 1 and 2, I'm not going to write it out. You can if you want to. It's just going to be equal to 0. I didn't quite give myself enough space to include that, so I'm skipping it for now. Anytime you actually have friction, you'll need to make sure you have friction included, the thermal energy included. Here, between points 1 and 2, we do not have friction. We're not including it. So if I go back and look at the table, I have no kinetic energy for point 1 and no elastic potential energy for point 2. So those are just going to go to 0. Now, if I look at my table, y1 is equal to y2, which is equal to 10 meters. So the values themselves are not equal to 0, but they cancel out. I'm going to have mgy minus mgy, and y is the same. So I'm just going to ignore them because I know they're going to cancel out. They're mathematically the same exact value. I'm lazy. I don't want to write that out. So because y1 is equal to y2, there is no change in gravitational potential energy, and I don't have to worry about it. When I subtract it from the final side to the initial side, it's just going to give me a 0. So simplifying everything down, I have my elastic potential energy at point 1 is equal to my kinetic energy at point 2. So going through and rearranging this, the halves are going to cancel out of k divided by m, x1 squared. I'm going to take the square root of that. So I was given all of these values for the spring stiffness constant, the mass, and the displacement that my spring is compressed. So I have 80,000 newtons per meter divided by my 100 kilogram mass times the 0.5 meters squared that I'm compressing the spring. Taking this and plugging it in, I got 14.1421 meters per second. Rounding to sig figs, 14 meters per second for the student. So this, what we are doing here is we are launching our student. So the second they come off the spring, they are moving about 14 meters per second. So we've used conservation of ideal energy here, just like we did in our previous lecture, to solve for his speed. Because our heights for point 1 and point 2 are the same, we are just able to ignore the gravitational potential energy. I didn't even write it in because I know 100 times 9.8 times 10 doesn't matter what side of the equation on, it's going to be the same exact value. So when I subtract it over, I'm going to get a 0. That is why I've crossed it out. It exists, however, it isn't relevant between parts 1 and part 2. I could do this on the ground and get the same exact answer. When it comes to comparing point 1 and point 3, I will need to include that gravitational potential energy. So we've calculated our velocity at 2. Now we want to go into part B, and we want to solve for the distance we are traveling on the incline. So I'm going to do a couple pieces of math before I go through and solve this question. So I'm going to first write out the conservation of energy. So I'm going to compare point 1 to point 2. So I'm going to have all the same energies I had before for point 1. When looking at 3, because I've now undergone some amount of friction, I'm going to have a change in thermal energy. So looking at the table, I can already get rid of a couple of things. And so now I'm going to have 1/2 kx1 squared plus mgy1, because again, I am starting 10 meters up. It's relevant, I need to include it when comparing to point 3 because I don't know what that height is. If I for some reason knew that y3 was equal to 10, I could get rid of them again, but I don't know that. Now I have mgy3 plus my change in thermal energy, which, let's just write the equation for that. It's mu k n delta s, or in this case, how I've defined it in my picture, L. So let's go back and let's look at the incline that we have. So I established that this friction part, if we go back to the picture, I identified it as L. Where our student is going to stop is at y3. So there is a relationship between y3 and L. So because y3 is opposite the angle, we would need sine. So y3 is going to be equal to L sine theta, where theta was again given in the picture as 30 degrees. We also can use this to calculate the normal force for our person, because we're going to need that for the thermal energy. Our person is on the incline, so that means that the normal force is going to be equal to mg cosine theta. Again, this is how we calculated the normal force on an incline when we introduced that 2 weeks ago at this point, I believe. So, these are the values. So that means that I can take these and plug them in to their locations. So doing that, I'm going to have nothing has changed for point 1. It's point 3 that's undergone quite some transformation. So this is now what my equation looks like. So before we continue on, let's explain what's happened so far. So initially I set up the conservation of the conservation of energy with thermal energy because now I have friction. I went through and I canceled all of the energies that I don't have. And what it left me with was an equation on the right side that had two unknowns. I do not know y3, and I don't know the length I'm traveling along the incline. By using trig, I can relate y3 and the length of the incline. Because I'm solving for the length of the incline my student travels up, I'm getting rid of y3 in my gravitational potential energy. So I've replaced it here. When looking at my equation for the thermal energy, I was given the coefficient of kinetic friction. I need to calculate the normal force of my student. Because I'm on the incline and how we set up our coordinate system to be, y being up, x being to the right. So for drawing out that normal force, we can use this coordinate system. That meant that the normal force is mg cosine theta. And plugged this in for the normal force value, and now we have this equation here. So it's from here that we're going to now be able to rearrange and isolate the length our student travels up the incline. So let's go ahead and do that. So the length the student is going to be traveling up the incline, I'm going to have my energy from point 1. Always get this distance wrong. I'm going to have mg sine theta plus uk cosine theta. Okay, I don't need that big of a line. If I go back and look at the question, I have the mass of my student. I have the spring stiffness constant. I know what the initial distance my student has compressed the spring. I know my initial height. The theta here is the angle of the incline I'm going up, which I have. I know that last I checked, it didn't say this was on any other planet, so I'm on Earth. And I was given the coefficient of kinetic friction for this student and that incline. I can now plug in all my values and solve for the length of the incline. So I'm going to have 1/2 times 80,000 newtons per meter. I originally compressed my spring 1/2 meter plus my 100 kilograms, 9.8 meters per second squared, times my initial height of the student, which was 10 meters. All that's going to get divided by 100 kilograms times 9.8 meters per second squared times the quantity of sine 30 plus 0.15 cosine 30. Taking all this and plugging it into a calculator, be careful doing it. I definitely screwed it up, so check your parentheses when doing this question if you're trying to do it all at once. Taking it and plugging it in, I got 32.0748 meters, or again, rounding to sig figs, 32 meters. So on this part of the problem, we've literally just plugged and chugged our way from isolating the length of the incline to getting the actual value for it. So before we're done with this question, there's one thing I want to do. I want to go through and make sure that this makes sense. So if I go back to my original image, it looked something really roughly like this. All right, so my student was up here, attached to some doom spring, and now they're over here. I should check and make sure that y3 should be greater than y1. And the reason this is the case is I have two potential energies when I'm looking at point 1. I have elastic potential energy and I have gravitational potential energy, whereas in point 3, I don't know why I was blanking on what number that was, I only have gravitational potential energy And yes, I technically have thermal energy. So, is this true? I guess that's what we're looking at. Maybe I have so much thermal energy it's not true, but it's something I'm curious about. Is my height greater, or is it less than, or is it equal? So let's just, what is the relationship between these? Well, I can go through, and y3 is equal to L sine theta. So if I take my L value with the extra sig figs, it's 16.037 for y3, and y1 is equal to 10. So it turns out, even with having thermal energy, we are going to go higher up than we initially started with because we have so much elastic potential energy, and not all of it is converted to thermal energy. This part's unnecessary to do in a problem-solving question. It's just kind of an interesting thing to look at. So this is going to wrap it up for this video and this example. The next video is another example, so I recommend checking that one out as well.